Welcome back to the deep dive. Today we're looking out into the universe, but finding something really weird, almost like a cosmic accounting error. Everything we see, touch, understand, stars, planets, us, that's just, well, the decoration.
It really is just a tiny fraction, isn't it? We're familiar with ordinary matter, what scientists call baryonic matter, but our best model of the universe, lambda CDM, it actually says about 85% of all the matter out there is something else, dark matter.
Completely invisible stuff.
Can't see it with telescopes, doesn't emit light or radio waves or anything. But it's gravity. Its influence is shaping everything.
Right, invisible, but you feel his presence everywhere. Now, you've probably heard the term dark matter, maybe seen it in headlines. Today, we're going to cut through some of that noise.
Yeah, synthesize the evidence.
Exactly. Our mission here is to lay out the really solid cross-reference proofs that dark matter isn't just some convenient fudge factor. It seems to be a physical reality.
And we'll look at how these different lines of evidence, they all point to the same conclusion. And also, why some of the alternative ideas like modified gravity really struggle to explain the big picture.
What's really striking, I think, is where this evidence comes from.
Oh, absolutely. It's from totally different scales.
Yeah.
You've got the way individual stars move within a single galaxy.
Okay.
Then you've got light bending over billions of light years.
Whoa.
And even echoes from the Big Bang itself, the cosmic microwave background.
And the key is they all kind of agree on the numbers.
That's the power of it. When these completely independent observations using different physics all converge on the same amount of missing mass, well, that gives you immense confidence scientifically.
Okay, let's dig into that. Pillar number 1. The weird way galaxies spin. We learn in school, farther from the sun, slower the planet. Pluto creeps along compared to Earth.
Standard orbital mechanics, yeah.
Yeah.
Gravity gets weaker with distance.
So astronomers naturally expected the same in spiral galaxies. Stars way out on the edges should be moving slower than stars near the bright center.
That was the prediction from just looking at the visible matter, the stars, the gas we can see. But that's not what they found. Even back in the 1920s, Jan Oort noticed stars in our own Milky Way seem to keep a constant speed way out. Then Fritz Zwicky, quite the character apparently, he looked at the Coma cluster of galaxies in 1933. He saw galaxies moving so fast, the whole cluster should have just disintegrated ages ago based on the visible mass.
And he actually coined the term dark matter.
He did, yeah. Dunkelmaterie in German. But partly maybe because of his personality, partly the state of data then, his idea was kind of ignored for decades.
Wow. So the biggest component of the universe's mass was basically sidelined because the discoverer wasn't popular. That's a lesson right there.
It really is. It wasn't until the 1970s that Vera Rubin and W.K. Ford did their landmark studies, starting with Andromeda, then dozens of other galaxies.
And they confirmed it.
Absolutely confirmed it. Irrefutably. When you plot star speed versus distance from the galactic center, you expect the speed to drop off, like a curve going down.
Right.
But instead, you get this almost perfectly flat line. The speed stays high, way out into the faint edges.
Which only makes sense if there's more mass there than you can see.
Exactly. Way more mass. The total mass has to keep increasing further out you go, proportionally to the radius, to keep those stars moving that fast. And since we don't see anything, it has to be invisible matter. A huge halo of it.
Okay, so that's a motion. Pillar 2, gravitational lensing. This sounds like sci-fi.
It does a bit.
Yeah.
But it comes straight from Einstein's general relativity. Massive objects warp space-time around them.
Right, like a bowling ball on a trampoline.
Good analogy. And light traveling through that warped space has to follow the curve. So very massive objects like galaxy clusters act like giant natural telescopes. They bend and magnify the light from things behind them.
But how do we know it's dark matter doing the lensing and not just, space dust or gas or something weird happening in our atmosphere?
Crucial point. Gravitational lensing has a unique signature. It's achromatic. Meaning it bends all colors, all frequencies of light by the exact same amount. If it were gas or dust or atmospheric refraction, different colors would bend differently, like through a prism. You'd see rainbows.
But you don't.
You don't. You just see distortion. Sometimes you see background galaxies stretched into incredible arcs, even multiple images of the same galaxy. Look at pictures of cluster Abel 2218. It's famous for this.
And the visible stuff in the cluster isn't nearly massive enough to cause those arcs.
Not even close. You calculate the mass needed to bend the light that much, and it vastly outweighs the mass of the stars and gas you can actually see. The difference. That's the dark matter.
And lensing comes in different flavors.
Yeah, broadly speaking, strong lensing is those dramatic arcs and multiple images we just talked about.
Yeah.
Very obvious. Weak lensing is much more subtle. You look at the shapes of thousands of distant galaxies in a patch of sky and look for tiny coherent distortions in their shapes. Statistically, you can map out the large-scale distribution of mass, the sort of cosmic web structure dominated by dark matter.
And microlensing.
Microlensing is different again. That's when a smaller, compact, dark object, maybe a primordial black hole, maybe something else passes directly in front of a background star. You don't see arcs, just a temporary, characteristic brightening of the star as its light is focused. It helps probe the clumpiness of dark matter.
Got it. Okay. Motion lensing. What's the third pillar?
The cosmic microwave background. The CMB. This is like the oldest light in the universe.
The afterglow of the Big Bang.
Exactly. Released when the universe is only about 375,000 years old, when it cooled enough for atoms to form and light could finally travel freely. It's incredibly uniform, but it has these tiny temperature fluctuations.
The seeds of galaxies and clusters today, right?
Precisely. And the pattern of those fluctuations, the size and strength of the hot and cold spots, what scientists call the power spectrum, is incredibly sensitive to the ingredients of the early universe.
You run models.
You run computer models of the early universe with different amounts of ordinary matter, dark energy.
Yeah.
And you see which recipe matches the actual CMB map we observe with satellites like Planck. And the models only match the incredibly precise data if you include a substantial amount of dark matter, about 5 to 6 times as much dark matter as ordinary matter. Models without it just fail spectacularly. They can't reproduce the peaks in the power spectrum.
And there's another piece from the early universe, something called BBN.
Right, Big Bang nucleosynthesis. This happened even earlier, in the first few minutes after the Big Bang, when protons and neutrons fused to form the first light elements, mostly hydrogen and helium, a little bit of lithium.
Okay.
The relative amounts of those light elements we see today, especially deuterium, heavy hydrogen, depend very sensitively on the density of ordinary baryonic matter back then.
And what does that tell us?
It tells us that ordinary matter can only make up about 4 to 5% of the total energy density needed to explain the universe's overall geometry, its critical density.
But we know from things like galaxy clusters and the CMB that the total matter density is much higher, like 30%.
Exactly.
Yeah.
So BBN says ordinary matter is only 5%, total matter is 30%. That leaves a massive 25% gap that must be made of non-baryonic matter. Matter that doesn't interact with light, matter that didn't participate in that early nucleosynthesis.
Dark matter.
Dark matter. And here's the kicker, the really beautiful convergence. The amount of dark matter needed to explain galaxy rotation curves, the amount needed to explain the gravitational lensing observations, and the amount needed to match the CMB fluctuations and satisfy the BBN constraints, they all agree. Look in the error bars, it's the same number. Roughly 85% of matter is dark matter.
That's pretty powerful. 3 totally different lines of evidence pointing to the exact same conclusion.
It's why the lambda CDM model, which includes cold dark matter, is the standard model of cosmology. It just explains so much so consistently.
And what about that initial confusion with the James Webb Space Telescope? Didn't it find early galaxies that looked maybe too big, too bright, challenging the model?
Ah, yeah, that caused a bit of a stir initially. JWST saw some surprisingly massive-looking and bright galaxies very early in cosmic history.
Which made some people wonder if galaxy formation happened faster than lambda CDM predicts.
Exactly. But further analysis seems to have resolved most of that tension. Part of it was realizing that early star formation could be really bursty, short, intense episodes, making galaxies temporarily look much brighter and more massive than they actually were overall.
Okay, so it was an illusion of sorts.
Partially, yeah. And another factor was the light from accreting supermassive black holes at the centers of these galaxies. That light was getting confused with starlight, artificially inflating the perceived mass and brightness.
So once you account for those effects...
Once you account for burstiness and active black holes, the population of early galaxies seen by JWST actually fits pretty well within the standard lambda CDM framework, which includes dark matter playing its crucial role.
Okay, so the standard model holds. Let's talk about structure then. How does dark matter actually shape the universe we see?
Well, think about the early universe again. It was hot, dense, ordinary matter, the baryonic stuff, interacts strongly with photons, with light. It feels radiation pressure.
Like light pushing on it.
Exactly. And in the early universe, that pressure would have tended to smooth out any small density fluctuations in ordinary matter. It would resist clumping up.
So if that's all there was, we'd expect a much smoother universe today. Fewer distinct galaxies and clusters.
Precisely. You wouldn't get the intricate cosmic web we observe. You need something that doesn't interact with light, that doesn't feel that radiation pressure, to start clumping up early on due to gravity alone.
But dark matter, acting like gravitational seeds or scaffolding.
Perfect word. Scaffolding. Dark matter comes first, creating these gravitational wells or halos, and then the ordinary matter gets pulled into those halos later, cools, condenses, and forms the stars and galaxies we see. Dark matter is the cosmic glue holding it all together.
Which led to the prediction of dark galaxies.
If dark matter forms these halos first, maybe some halos just never managed to attract enough ordinary gas to form stars, or maybe they lost their gas. So you could have clumps of dark matter out there with very little or no visible counterpart.
And this ties into the missing satellites problem.
It does. Computer simulations based on lambda CDM predicted that big galaxies like our Milky Way should be surrounded by thousands of smaller dwarf galaxy companions orbiting within our large dark matter halo.
But we only saw a few dozen.
Yeah, for a long time we only knew of about 60 or so visible dwarf galaxies orbiting us. A big discrepancy.
Were the simulations wrong?
Turns out, the simulations were predicting the number of dark matter subhalos, not necessarily visible galaxies. We were looking for the bright baryonic components, but maybe many of those subhalos are indeed dark galaxies.
Invisible oranges, not visible apples.
Exactly. And techniques like gravitational lensing are now actually starting to detect evidence of this lumpy substructure, these smaller dark matter clumps, consistent with the predictions, like finding hundreds of candidate dark galaxies in the Coma cluster.
Okay, so we have galaxies that seem to be mostly dark matter. What about the opposite? Are there galaxies without dark matter?
Fascinatingly, yes, or at least with very, very little. There are a few recently discovered ultra-diffuse galaxies, like one called NGC 1052 DF2, or just DF2 for short.
And what's weird about DF2?
Its stars are moving incredibly slowly. Based on its brightness, you'd expect its stars to be orbiting much faster if it had a normal dark matter halo. They measured speeds around like 8 kilometers per second.
Whereas normally it should be.
Maybe 30 kilometers per second or more, depending on the exact assumed halo mass. It seems like this galaxy somehow formed without much dark matter, or perhaps had it stripped away by interactions with its giant neighbor galaxy, NGC 1052.
And the fact that such galaxies can exist actually supports the dark matter idea.
Paradoxically, yes. It shows that dark matter isn't just some modification of gravity that applies everywhere. It's a separate substance that can be present or absent. DF2's existence and its slow rotation confirms that usually dark matter is the component providing the extra gravity needed to hold galaxies together and make stars orbit faster. Without it, like in DF2, things move slowly and the galaxy is probably quite fragile.
Okay, but the absolute killer evidence, the thing that really seems to separate dark matter from modified gravity, that's the bullet cluster, right?
The bullet cluster is, for many physicists, the smoking gun. It's actually two galaxy clusters that have collided, or rather, passed through each other at immense speed.
A cosmic crash.
A huge one. And we can observe the aftermath using different methods. X-ray telescopes see the hot gas, which makes up most of the ordinary matter in the clusters.
Okay, where's the gas?
The gas from the two clusters smashed into each other and slowed down due to drag forces, like friction or ram pressure. It forms this big, central, bullet-shaped shock wave. You see it in pink in the famous images.
Got it. Pink is the ordinary matter gas, slowed down in the middle.
Right. But then you use gravitational lensing to map out where most of the total mass is.
And where is it?
It's not with the gas. The lensing map shows two distinct clumps of mass, shown in blue in the images, that seem to have passed right through the collision zone almost undisturbed, located ahead of the slowed-down gas clouds.
So the bulk of the mass, the dark matter, just ghosted right through.
Sailed right through. Because dark matter, whatever it is, interacts very, very weakly with itself and with ordinary matter. It doesn't feel drag forces like the gas did. It primarily interacts through gravity.
Wow, so you have a physical separation. The ordinary matter got stuck in the collision, but the dark matter kept going.
Exactly. This observation is incredibly difficult, if not impossible, to explain with theories that just modify the law of gravity. Modified gravity acts where mass is. If you modify gravity, the strongest gravitational effects, the strongest lensing, should be centered on where most of the ordinary matter, the gas, is.
But it's not. It's centered on these separate clumps that pass through.
Correct. The bullet cluster provides compelling evidence that dark matter is a real physical substance, a type of matter that is largely collisionless. It really pushes us towards thinking dark matter must be some kind of new particle.
Which brings us to particle physics. If astrophysics demands this stuff exists, does particle physics actually, have room for it? Or does it mess up their theories?
Actually, it's the opposite. Particle physics also seems to need new particles beyond the standard model. The standard model, while incredibly successful, is known to be incomplete. Well, for several reasons. There are theoretical ideas like supersymmetry, often motivated by string theory, which propose a whole set of partner particles for the ones we know. The symmetry would solve some theoretical problems and often predicts stable, weakly interacting particles, potential dark matter candidates.
Okay, so supersymmetry needs new particles. Anything else?
Yeah, there's the puzzle of the Higgs boson's mass. It turned out to be much lighter than many theories predicted. Its relatively low mass is considered unnatural unless there are other new particles interacting with it in just the right way to stabilize it via quantum corrections.
So new particles could solve the Higgs mass problem and be the dark matter.
Potentially, yes. It's this beautiful potential synergy. Dark matter isn't just solving a problem for astronomers looking at galaxies. It could simultaneously be solving fundamental problems within particle physics itself. There's also this huge gap, like 16 orders of magnitude, between the smallest scales particle accelerators can probe and the theoretical Planck length where quantum gravity must kick in. Many physicists suspect new physics, new particles must lie in that vast, uncharted territory.
But if dark matter is a particle, maybe even one predicted by these theories, and there's so much of it, why haven't we found it yet? Decades of searching in labs.
That is the billion-dollar question, isn't it? Many searches focused on a specific type of candidate called WIMPs, weakly interacting massive particles. They were theoretically favored, perhaps interacting via the weak nuclear force.
But those searches have largely come up empty.
They have, at least for the simplest WIMP models. This has led people to think more broadly. Maybe dark matter doesn't interact via the known forces at all, except gravity. Maybe it lives in a dark sector.
A dark sector, like a parallel universe sort of thing.
Kind of, yeah. Imagine a whole set of new particles and maybe even new forces that only interact very, very weakly, or perhaps not at all, with our standard model particles, except through gravity.
So it's right here, all around us, but invisible because it doesn't use electromagnetism or the nuclear forces we're familiar with.
That's the idea. It would be its own interacting world, overlapping with ours gravitationally. This fits nicely with some high-level theoretical concepts like eternal inflation in cosmology, or the many-worlds interpretation of quantum mechanics, which naturally suggest a multiverse with different sectors or universes that might have different properties. Maybe we can only interact with this dark sector via gravity, or perhaps with some very weak portal interaction, mediated by hypothetical particles like dark photons or axions.
So the search needs to broaden beyond just WIMPs.
Definitely. We need to consider particles with vastly different masses, different interaction types, maybe even composite dark objects or primordial black holes. The possibilities are wide open.
Okay, so the particle idea has strong legs from both cosmology and theory. But we should talk about the main alternative that tries to avoid new particles. MOND, modified Newtonian dynamic.
Right. MOND basically says, maybe there's no dark matter, maybe we just don't understand gravity correctly on large scales or at very low accelerations.
It proposes that Newton's law of gravity itself changes in regions where gravitational pull is extremely weak, like the outskirts of galaxies.
Exactly. And MOND is actually remarkably successful at fitting the rotation curves of individual spiral galaxies. That specific flat line we talked about, MOND can reproduce that quite elegantly without invoking dark matter within the galaxy itself. That's its strength.
But you mentioned earlier it has problems. If the bullet cluster is the fatal blow, why do people still work on MOND?
Because of that success on galaxy scales, it suggests something interesting is happening at low accelerations. However, MOND runs into serious trouble on other scales.
Like where?
Well, on smaller scales, tests looking at the orbits of wide binary stars, where accelerations are low, find no deviation from standard Newtonian gravity. That contradicts MOND's basic premise.
Okay, fail small scales. What about large scales?
On the largest scales, like galaxy clusters, MOND alone just doesn't cut it. Even after modifying gravity according to MOND's prescription, you still need a significant amount of additional unseen mass to explain the observed velocities of galaxies within clusters and the strong gravitational lensing.
So MOND needs its own dark matter.
Essentially, yes. or at least some form of unseen mass, maybe sterile neutrinos or something. It reduces the amount needed compared to standard gravity, but it doesn't eliminate it entirely in clusters. And critically, as we discussed, MOND just cannot explain the separation of mass seen in the bullet cluster.
Right, the lensing peak being offset from the gas.
That remains a fundamental problem for MOND. Plus, MOND originally made predictions about gravitational waves traveling at different speeds from light under certain conditions, but observations of merging neutron stars showed they arrived simultaneously, ruling out many simple versions of MOND.
Okay, so MMD has significant issues. What about hybrids, like superfluid dark matter? That sounds exotic.
It is. It's an attempt to combine the best of both worlds. The idea is that dark matter exists as particles, but in the very cold, dense centers of galactic halos, these particles condense into a quantum state called a Bose-Einstein condensate, basically, a superfluid.
A liquid with zero friction.
Exactly. And within the superfluid, collective excitations like sound waves or phonons can mediate an extra force between the ordinary matter particles.
And this extra force mimics MOND.
It could be tuned to mimic MOND's effects on galaxy rotation curves, potentially explaining MOND's successes while still being fundamentally a dark matter theory that behaves normally, like collisionless particles, on larger scales, potentially resolving the cluster and bullet cluster problems.
Interesting. But does it work?
It's a developing idea. Challenges include figuring out which particles could form such a superfluid, how it forms naturally in the universe, and making sure the theory works consistently within the framework of general relativity, curved spacetime. It shares some features with other ideas like dark plasma hypotheses. It's definitely an active area of research trying to bridge the gap.
Okay, so wrapping this up, we've seen the evidence converge. Galaxy rotation, light bending from unseen mass, the blueprint in the CMB, the need for structure formation, the dramatic separation in the bullet cluster. It all seems to point overwhelmingly towards dark matter being real.
The evidence is diverse and compelling, yes. The debate among most physicists isn't really if dark matter exists anymore, but rather what it is.
And the standard lambda CDM model incorporating cold dark matter seems robust, surviving challenges like the initial JWST results.
It does. But the lack of direct detection in labs tells us we might need to think beyond the simplest WIMP candidates. Our experimental searches might have been too narrow. We need to explore these ideas of dark sectors, different forces, maybe a much wider range of particle masses or interaction types.
It makes you think. It took science centuries to really accept atoms, decades to finally pin down the neutrino and the Higgs boson after they were predicted. Maybe we're a bit impatient expecting to find a particle that barely interacts with our world within just a few decades.
It's a very fair point. Our detectors, our experiments, even our brains are made of ordinary baryonic matter. We're trying to perceive something that constitutes the other 85% of matter using tools built from the minor 15% fraction. It's inherently difficult.
So the final thought, perhaps. The sheer necessity for these new particles coming from both the cosmos and fundamental theory, it makes that idea of a dark sector, maybe even a multiverse, seem less like science fiction.
And more like an increasingly unavoidable feature of reality. The universe is likely far richer and more complex than the part we can directly see and touch. That invisible 85% holds profound secrets waiting to be uncovered.